Chapter 17 examples for cost accounting. So Chapter 17 was all about quality analysis or looking at quality. So in this first example, we're going to do statistical analysis to look at the quality loss function for a computer chip industry. So we have a computer chip. We have our target value of 0.2 millimeters, and then we have tolerance allowed of 0.002, which gives us a top range and a low range for the millimeters of distance between two adjacent pins. And anything that doesn't fall within that range is rejected or thrown out. So in this chart here, we have the quality control manager has taken a sample of 100 chips from the production process and has the following results. He has the measurement of the distance between the two pins and the frequency within the 100 of times at which that occurs. And we're going to look at the Taguchi quality loss function from the chapter. So first, we're going to compute the nearest whole number, the value of k, in that loss function. So when we're looking at the value of k from the Taguchi loss function, that value is our total quality cost divided, so $20, divided by the tolerance allowed squared. So for k, we have $20 divided by the tolerance allowed squared, or to the second power. So our value is $500 billion. That's the whole number loss in our Taguchi cost function given this information. What we're trying to do is figure out what the estimated quality loss for each of the observed measurements is, and then calculate the expected or average loss per unit from the production process as a whole. So what is our average loss per unit for these 100 samples based on the probability of these measurements happening? So X is our measurement. And L times X equals K times X minus our target value, and that to the second power. So we're going to lock the cell with K in it so we can copy that formula down. Let's also lock the target value cell. Now we're going to look at the probability of that happening. So the probability is F times X. So when we're looking at the probability, this is the frequency divided by 100%. We take our LX line times the probability of that happening, and we get values for the production process. We add those values together, and the the average loss per unit for the production process as a whole is $12.75. Next, we're going to determine the square of the deviation of the mean value from X from the targeted value. So first, we have to calculate the mean of average value of X. So before we can look at the square of the deviation. So first we have to look at what the mean of X is. When we calculate the mean of X, this is our measurement times the probability of the frequency happening. Carry that down and sum and we get this total value. That is our mean average value of X. So to get the square of deviation from the targeted value, we are going to take the mean that we just calculated minus the targeted value of 0.2, and then we're going to take that out just a few more. And we're going to square that, or to the power of 2. We have to take it out 12 points to get the numbers for it. Now we can use this information to determine the variance of the observed values and the expected average loss per unit of the process. So for this calculation here, we take X minus our mean, then square that value and take it times the f of X, or our probability. Then we have to change that to a number because it automatically gives us a scientific number because of how many zeros we need in that. So we're going to make this cell bigger, and we're going to take all of our decimal points out. We sum this value. And now that we have the variance of the observed values of X around the mean value, we can calculate our expected per unit loss of the process. So that expected per unit loss, take our value times the variance plus our square of the deviation and get $12.75. So on average, That variance is $12.75. In our second example, we're looking at the manufacturing cycle time. So we have this graphic from chapter 14 where we talked about customer response time, which is the time it takes from the time a customer places an order for a product until they have received the product. Part of that is the manufacturing cycle time, which is also called the manufacturing lead time. So we have two examples here. We're looking at two manufacturing process layout options. So this is how we lay out the actual structure of the floor of our manufacturing process. And we have under alternative 1, our total time is 166 minutes. And under alternative 2, our total time is 154 minutes. So number 1 was already given to us in the information. The manufacturing lead time or manufacturing cycle time per batch is 166 for alternate 1 and 152 for alternate 2. Part 2 says, determine the manufacturing cycle efficiency for each layout. So the manufacturing cycle efficiency measurement is the amount of value added time divided by the total manufacturing lead time. So what of these activities is value added? Add those together and divide them by the total time. So non-value added items are setup. This is the time it takes to set up a machine to run a batch. Movement. So this is the time our factory employees are moving materials and work in process around the floor. Waiting. This is when our people are just standing around waiting for something to happen. And inspection. None of these are value added from the customer's perspective. So our total non-value added time, 86 minutes for alternative 1 and 94 minutes for alternative 2. The processing time is the only value added activity of this process. So 80 and 60. So our manufacturing cycle time is this value added time divided by our manufacturing lead time. Our goal in manufacturing for the manufacturing cycle time and this manufacturing cycle efficiency value is to get that number as close to 1 as humanly possible. So if we were just looking at the manufacturing cycle efficiency time, alternative 1 is the best option for us. In this example, we are a technology company, and we're looking at moving from our current manufacturing system, which is just a standard manufacturing system, to a just-in-time structure. Now remember, with just-in-time, it's not just an inventory management. So with just-in-time inventory management, we only produce goods when orders are placed for them. So we don't stock inventory for sale. The other parts of just-in-time inventory management are that we are removing non-value added activities, we're increasing our manufacturing cycle time, we're reducing the amount of time that people are standing around, and we're working for 100% quality in all of our products. So what this problem asks us to do is look at all of our information for before and after and decide if we want to take on this system. So do we want to move into a just-in-time inventory manufacturing-based system? I already talked about how it's different from a conventional system. Now we want to look at the numbers. So first we have our estimated sales after the just-in-time. Well, before we're selling 40,000 units per year. We see that we expect a sales increase of 25% because of the improvements in cycle time and the improvements in product quality that come from a just-in-time system. We believe we're going to see an increase in sales of 25%. So we would take to project our sales out that 40,000 times 1.25. So our predicted sales in units after are 50,000. Now we're going to look at what is our estimated annual decrease in contribution margin. So what is our contribution margin from the new system versus our contribution margin in the old system? Remember, contribution margin is sales minus various costs. So we are going to look at sales price. So our selling price per unit would be $70 minus the variable cost per unit times this projected forecast of 50,000 units. And we're going to subtract that from our previous information, which is $70 selling unit minus $50 variable cost times 40,000 units. So what we see is that we're going to have a $950,000 annual increase in contribution margin. Next, we're going to look at what is our decrease in annual inventory carrying costs. So our current carrying costs are that we hold 4 months worth of direct materials, 3 months worth of work in process inventory, and 2 months worth of finished goods inventory. And then we have our average cost per unit. So to determine what our current or prior to just-in-time carrying costs are, we would take those 40,000 units in sales times the carrying costs. We're doing direct materials first, and then times 4 divided by 12 months. And for work in process inventory, the same, 40,000 units times our work in process cost of $25 times the 3 months divided by 12 months. And for finished goods inventory, 40,000 units times $40 per unit times 2 months divided by 12 months. So our current average inventory holdings, $716,667. The post holdings, what information that we have is that our inventory holding cost, we can cut that in half. So the months, then we can cut in half from current levels. So our new costs will be the new 50,000 units times the price stays the same, but now instead of 4 out of 12 months, we're going to have 2 out of 12 months because we cut the holding time in half. And for work in process, 50,000 units times $25 cost times 1.5 divided by 12. And for finished goods, 50,000 units times $40, 40,000 units times 1 divided by 12. So we're going to have a difference in inventory holding, 227,000. There we go. Our inventory holding cost rate is 10% before and after. So 10%, we take our savings times the 10% holding cost, and we have an estimated decrease in annual inventory holding costs of $36,666.67. Next, we're going to look at that increase in our annual lease cost. So we currently are paying $500,000 a year for our lease, and this new equipment is going to require $1 million a year lease. So $1 million minus 500,000 is 500,000 in our increase in the annual lease cost. So when we're looking at our annual net benefit of switching to just-in-time, we have an increase in contribution margin plus savings in holding costs minus the annual increase in our lease cost. If we want to round that up to the whole dollar, we see that our annual net financial benefit cost, so we'll have cash flows of $486,667. The next one asks, what is the first year net financial effect of investing in the new equipment? Well, because we have a one-time penalty, we would have to reduce our yearly cash flows by that one-time penalty. So in year one, our cash flows would be the $486,667 minus this one-time penalty of $275,000. Our last example is a cost of quality statement. So for this cost of quality statement, we are looking at the 4 different costs of quality for any organization. So our 4 costs of quality, if you remember from the chapter, are prevention, appraisal, internal, and external failure costs. Prevention costs are those items that we use to prevent quality measures anyway. These are things like training our employees, certifying vendors, value engineering of products. Appraisal costs is testing and inspection costs. Internal failure costs are scrap and rework and things that happen to the quality of the product internally. And external failure costs are the failures of a product after it gets into the hands of a customer. So we're going to create this statement of our cost of quality. So we start with the amount of sales. We have sales in 2019 of 16,000 and sales in 2020 of 20,000. Then we have our prevention costs. So we're going to sort each one of these out. First, we have materials, production, and finished product inspection. Well, inspection is an appraisal cost. So all of these are appraisal costs. Next, we have preventative equipment maintenance. Well, that's right in the title. Preventative is a preventative cost. Scrap is an internal failure cost. Would move scrap down to internal failure. Warranty repairs are external failure costs. So if people are coming back and using the warranty, that means the customer already has it, and so that is an external failure because the customer has it. Product engineering is a prevention cost. So when we redesign the product so it's more efficient or has higher quality standards, we use different materials or other various things. Vendor certification is a prevention. This is when we make sure all of our suppliers are sending us the best materials possible, and we only buy from vendors that are certified. Returned goods, this is an external failure because that means our customers have the product and they're returning it because they're dissatisfied with it. So, and training of factory workers is prevention. Product testing is appraisal. Field repairs, that means that the customer already has it and we go to their location to repair it. So that is an external failure cost. Rework before shipment is internal. We found the quality issues before it left for the customer, but it still had a production issue, so we failed. Product liability settlement, so that means that we've been sued for liability. That's external. And emergency repairs and maintenance are an internal failure cost. So regular machine maintenance is a prevention cost, but emergency repair maintenance is an internal failure cost. So we add up our totals. So we sum up both years' amounts so we can analyze them side by side and make comments on our results. And so that we can see how much money we are spending for various quality measures, where we might be having issues with quality that need to be addressed. we take each prevention measure divided by sales. And what we can see here is that we've more than doubled our prevention costs, and we've seen a big reduction in appraisal costs and internal failure costs and external failure costs. So that is what we would hope to see. We would hope by training our employees, increasing money that we spend towards value engineering and certifying our suppliers, that by making an investment in prevention, all of our other quality costs would go down. We would not have as much failure costs or need for extra inspections. If we were going to do this sensitivity analysis, we would look at the 2020 amounts. So this is our information here for 2020. What are our total amounts? So our sales are 20,000 and prevention costs 530, appraisal costs 405, internal failure 575, and external failure 630. Total cost quality 2,140. So what we're looking at here is this sensitivity analysis. So what if all of this stuff happened? If we have an increase of 5% in sales, so sales times 1.05, we have an increase in total prevention costs of 6%. And then we predict there would be no change to our appraisal costs, but our internal and external failure costs would be reduced. So internal times 1 minus 0.6. And a 50% reduction in our external failure costs. So what would that be as a result for all of our costs? So as a percentage of sales, so then we see that with another increase in our prevention costs, we could further reduce our other costs and bring our total cost of quality down to from 10.7% to 7.2%.